Hello students, and welcome to this episode of Chemistry in My Kitchen. We're going to look at some ideal gas laws today. So we're going to relate temperature to pressure to volume and see how that makes some interesting phenomena happen. Now we're going to look at Charles's law. Charles's law comes from Jacques Charles, a French scientist back in 1787, who decided that maybe, just maybe, volume and temperature had something to do with each other. So he was sitting around his house, kind of like what we're all doing, and he decided he was going to use a can to test his theory at two different temperatures. So here we have the modern version. We have a can heating up and a bowl of ice water to provide our cold temperature. All right, we have our can that's been heating up in our boiling water. And we're going to try and crush it using just the power of changing the temperature. So hopefully that water vapor inside the can needs to be heated all the way up. Let's see if we can do it. Woo! That was quick. So we're back here with our can crushed by Charles's law. We related volume to temperature, but you'll notice that it crushed, which means maybe it had something to do with pressure too. You remember pressure from Boyle's law. Seems like they're all related. And if we think about kinetic molecular theory, when the gas was heated, those particles were moving really fast, pressing on all the walls of the can, keeping it expanded. And then when we closed off, so we had the same number of molecules in the can, but the temperature cooled, it started to condense those molecules, just like in our Cartesian Diver. The molecules became more dense, so they weren't pressing on the walls anymore, and the can imploded. Next up on Kitchen Chemistry, we're going to look at Boyle's law. As you guys might know, I love scuba diving. Check out my other videos. And Boyle's law is super important when you're scuba diving because it relates the volume of a gas to the pressure that you're under. And as you go deeper and deeper underwater, you're under more and more pressure. So in a minute, we're going to take a look at how that affects gas and why that needs to be something you pay attention to when you're scuba diving. So in this bottle, I have what's called a Cartesian Diver. And it's a glass tube that's filled with air. And then I have it inside a water bottle. And as I squeeze this water bottle, I'm increasing the pressure. As I squeeze it more and more, you notice the Cartesian Diver dives to the bottom of the bottle. And then as I release pressure, it comes back up to the top. Increase pressure. Do you notice anything that happens as I increased the pressure? And release pressure. Increase pressure, decrease pressure. Increase pressure, decrease pressure. So we're looking at the increase in pressure and the change in volume of the gas that's inside the Cartesian Diver. As that gas is compressed, it becomes more dense, causing the Cartesian Diver to dive. This relates to scuba diving because as you go underwater, your body and the gases that you're breathing are under pressure. And as you come up, they're going to expand. So when you're at depth, you're getting things like nitrogen, oxygen, all those gases are dissolved in your bloodstream in teeny tiny bubbles. And as you come up, if you come up too quickly, those bubbles can expand to a size that doesn't fit through your veins and arteries and capillaries, and they can cause a blockage, not allowing blood to continue flowing through those places, which basically causes a stroke. It's called an air embolism. So it can cause a stroke, it can cause blood to not reach other extremities, and if you have that problem, you immediately need to go to a decompression chamber where they're going to put you back under pressure and then slowly and controlled In that chamber, they're going to release the pressure over a period of many hours, causing those bubbles to compress and then diffuse through your body so that those bubbles are not as large when you come back up to regular pressure. Here we have a second example of Boyle's law where I've put some water in a vacuum chamber and I've sucked all the air out, creating a vacuum, meaning there's no pressure. And because there's no pressure, we know according to Boyle's law that the volume is going to increase, meaning that this liquid is going to start turning into a gas, i.e. it's going to start boiling. So you can watch this video and see this liquid begin to boil. You'll also notice, if you were here to feel it when we took it out of the vacuum chamber, that it's nice and cool because as you release pressure, we know that according to Charles's law, temperature is going to decrease. So you can see a little bit of Charles's law in this experiment as well. So Charles's law was pretty fun, and I wanted to show you Charles' law going in the other direction. So we're going to start with a relatively cool object, this bar of soap. And this bar of soap is a little bit special because it's a whipped soap. And whipped means that it has a bunch of air bubbles in it. So all those tiny air bubbles give us tiny pockets of gas that we can then heat up in the microwave. So what do you think's going to happen? Here I have our bar of whipped soap, and I'm going to put it in a microwave-safe bowl. And I'm going to put it in the microwave for 2 minutes so we can heat it up and see what happens. So we gave our soap 2 minutes in the microwave, and I'm going to open it up, and it definitely got a little hot. So I'm going to carefully take it out of the microwave oven and show you. It smells great too. Now as it cools, it's going to shrink just a little bit, and you can touch it, but you want to wait until it cools down a little bit. So I'm going to give it about 2 minutes to cool off before we take a closer look. Alright, so here's our cooled and fluffy soap, and you can pick it up. It's pretty crumbly. It's super fluffy because all of those air bubbles expanded. Ooh, it's like a cotton ball almost. And it still cleans like soap, so you can definitely still use this if you make it at home. One of the fun things you can do with it is add a cup of hot water, and then you can add about a roll, well, a half a roll to a roll of toilet paper, a little bit at a time, and you can make clean clay, which is kind of like clay, but it's soap, and because you use toilet paper, it's totally biodegradable, so it can go down the drain, and that can be fun to model into cute shapes. So yeah, there's Charles's law. All right, so welcome to my first experiment. Good thing it's kitchen chemistry. That is 100% food safe dye. It will not hurt my cat who loves his new water bowl. All right,
So we're going to make some observations of what happens when I light these 3 candles. And then I'm going to place this jar over the top.